Apartment service sizing. In this presentation, we're going to be looking at how the Canadian Electrical Code determines the total service for a typical smallish apartment. Important rules that we will need to be referencing are 8202, 8106 subrule 2, 8106 subrule 3, and 8108 subrule 3. Let's get going. Now, it's important for us to realize that an apartment will have three distinct conductors that require sizing. And that's important for us to be aware of because the code itself does not explicitly make this brutally clear. It takes a little bit of know-how to see where that division takes place within the rules. So here is a typical field assembled main apartment service where we have the service disconnect, the CT metering cabinet, and the meter base that is supplied by the CTs. We have an apartment public panel, often referred to as a house panel. And then we have all of the different apartment suite panels, so disconnects, I should say. So they're all going off to their individual suites. Now, the three different conductors that require sizing are done independently. The first one, of course, is this, apartment main service. That, of course, is a distinct conductor that will need to be sized. The next ones are all of the individual sizes of the actual apartment suites. And finally, we need to size this, the public panel for the apartment shared loads. So suite feeder conductors, public panel feeder, and main service conductors. When we go to calculate these, the complexes can vary in size significantly. Smaller apartments may only be serviced with a nominal 120 240 volt single phase system, while larger complexes are supplied with 120 208 three-phase. In addition to this, some electrical load within an apartment will be considered continuous and others not. So what's important is that we recognize what the divisors are and what type of equipment is typically utilized. The main apartment service, if we have supply of three-phase, four-wire, the load is considered continuous. The equipment is typically rated for 100% continuous operation. And due to that, there is no need to go about adjusting the end amperage to accommodate an 80% rated overcurrent. The public panel feeder in a three-phase, four-wire apartment, the load is considered continuous. The equipment is typically rated for 80% continuous operation, meaning the panel board and the disconnects that supply the public panel are typically 80% rated. In this situation, you would then need to increase or divide by 0.8 the amperage to get a larger wire. And finally, suite feeders in a three-phase supplied apartment are given two phases, three wire. So two phases and a neutral. The load is considered non-continuous because it's a residential suite and the equipment is typically rated for 80% continuous operation, meaning we don't have to adjust the overall amperage to facilitate increasing the size of the wire for continuous operation. Now, it's also important to know that there may be some different multiplier. So the individual suites inside the apartment supply typical residential loads, meaning they do not receive three-phase four-wire. Apartment suites are one of the unique loads in the electrical industry that require a two-phase three-wire feeder supplied from the three-phase service. Each suite receives two-phase conductors and a common identified, and this provides the line-to-line voltage of 208, which is slightly lower than the more common standard single-phase value of 240. There are no problems with this arrangement due to the types of loads using this voltage in a residential setting, and loads that include baseboard heat, clothes dryers, ranges, all that stuff will typically be rated with both 240 or 208 nominal system voltage ratings. The only difference in operation to the consumer will be a slightly longer time for full heating to be achieved. So let's take a look at an overview of suite feeder conductors. They are very similar to what we see in the residential single dwelling application. 82021A, item I to III is basic load. 82021A IV to VII is specific loads, giving us total watts and total calculated watts. We take the total calculated watts divided by the system voltage, which, if it is single phase, is 240, If we're receiving two-phase from a three-phase system, it's 208, and that gives us our calculated service ampacity. We then refer to 1B because the service or the consumer service feeder is really, again, a determination on which two numbers are larger, total calculated amps or default amps. Larger amp value equals the minimum service demand, and we use table 2 or 4 and 13 for the overcurrent. Public panel feeder conductors are slightly different. The only rule that is utilized here is 8202 subrule 4. Now, this is commonly referred to as a shared or house loads that all residences share the use and cost of. All loads are taken at their rating, and applicable demand factors. So section 62, the heat and AC 8106 subrule 3, 8400, table 38 for electric vehicle chargers. If the objects that we've just identified there are in the common space and paid for by everyone, they're under 8202 subrule 4. All we do here is we calculate the sum of all the common use loads, total watts. The minimum public panel demand divided by the system voltage equals the public panel amperage. Now remember, if the apartment is three-phase, the public panel will receive a three-phase 4-wire feed. So that means your voltage is 208 times root 3. If the apartment is single-phase, then obviously public panel receives a single-phase 3-wire, divisor is 240. The public panel is always considered a continuous load, and due to this, the public panel equipment continuous operation rating must be known. So it can be 80 or 100% as per 8104. In the field, most public panels will be 80% rated for continuous operation. So just to remind everyone as to the process from 8104, if we're using conductors in conduit, we would take the public panel amps divided by 0.8, get a slightly larger conductor, and size the overcurrent from table 13 based on the slightly larger conductor. If the public panel equipment is 100% rated, then there is no adjustment that is necessary. We're not going to be using single conductors to supply the public panel, so don't worry about that. So let's look at an overview of the main apartment service conductor calculation. 82023AI to VII takes the minimum single unit suite service demand and subtracts or removes all the climate, which is the heat and AC. We then apply a sliding scale calculation to the new lower single unit demand, and that gives us our total unit watts, which should be about the bulk of the load for the apartment. 82023B calculate the sum of all the heat in the complex. That means we take all the heat together and all the AC together, and we determine which one is larger if they are operating at the same time. If the total is over 10 kilowatts, of course, we go to 62118 subrule 3, and we get the total climate demand. 82023D, common use electric vehicle chargers are added, table 38 values. And 82023E, common use loads other than EV chargers are taken at 75% of their rating. So things like exterior lighting, irrigation, all of that stuff. So we add all of that together, we get the minimum service demand, and the minimum service demand is then divided by system voltage. And again, depends if it's three-phase or single-phase to get our single or our minimum service conductor ampacity. And due to the rule 8202 having various portions within it, indicating that different portions of loads are continuous, usually the main service equipment is rated for 100% continuous operation, and that's what we will be using for our examples in this presentation. Conductor and OC sizing are taken from table 2 or 4 and 13. Well, let's take a look at an example. So we've got an apartment service calculation example here. It is a 22 unit apartment complex. We have a number of common loads, including 10 5 kilowatt electric vehicle charging stations. And then we have 3 different sizes of individual suites. We have A, B, and C. So I'm going to go back up here, show you the total for the common loads and all the information, you can take it down. And now I'm going to move down a little bit and again show A, B, and C. Let you take down that information. Pause the video here, calculate everything out, and then unpause it, and we can work through the answers together. All right, so for this installation, the main service equipment is rated for 100% continuous operation. All other equipment is rated for 80% continuous operation. Let's look at the first step. Well, the first step is going to be ensuring that we have the right size conductors supplying each one of the suites. Now, there's a whole bunch of suite A type, B type, and C type. So we're going to do the calculation for A first by using 82021A and B. 150 meters squared total area. And remember, the total area of an apartment suite is calculated at 45 meters squared for the first, 45 meters squared for the second, and any portion thereof that is in excess of 90 meters squared is taken at 1,000. So that means we have 6 kilowatt basic load. We have 6 kilowatt of heat inside that unit, and the range is 7.2 kilowatts, giving us 19.2 kilowatts. That means 92.3 amp minimum service ampacity. Now, table 2 and 13 are utilized to select a conductor and an overcurrent. Let's look at suite B. It's slightly smaller, therefore the basic load is a little bit less, 5 kilowatts. 5 kilowatt heat, 7.2 kilowatt range, giving us 17.2 kilowatt total basic demand, or total demand rather. Divided by, again, 208, because this is a 3-phase 4-wire supplied apartment service, and the suite is getting single phase, or you could say 2 phases, 208. We get 82.6 amps, which we take to table 2 for 85 amps, and table 13 for a 90 amp overcurrent. Finally, suite C is 80 meters squared, and we have basic, heat, and range, very small amount of heat. 55.2, and we can see here the minimum service feeder ampacity, 60 amps, because obviously we compare it against 82021B and see that 55 is too small. Table 2 and 13, number 6 AUG, 65 amps, and table 13, 70 amp overcurrent. Well, let's take a look now at the next step. The next step is to calculate the main service conductor size. So, suite A, 19.2 kilowatts. Suite B, 17.2 kilowatts, and suite C, 12.48 kilowatts. Now, this isn't the same as what we saw in a row house feeder. The row house feeder required that we utilized a inflated value, but 12.48 is going to be what the calculated value was from the previous step of suite C. I just completely misspoke. Disregard exactly what I said for the last 10 seconds. Suite C, 12.48 kilowatts, is actually the kilowatt rating of 60 amps times 208 volts. We use the minimum required service ampacity for suite C. We did not use the calculated. And again, just to confirm, I'm going to go back up here. There's suite C. Remember, we calculated 11.5. Well, the minimum was 60. And if we take 60 and multiply it by 208 volts, we end up with this number down here, 12.48. All right, so that aside, what we're going to be doing is taking all of these units, removing all of the climate out of them, and then applying it to our sliding scale calculation. This one place in the entire calculation is where most people lose it and they get the wrong answer, and it's simply because we're not organized enough. I write everything out when I do this longhand, the first one, and I write the kilowatt value at 100%. The second two, 13.2 at 65%. Notice I've got one here, 13.2, and this one here, 12.2, right? So 12.2 is right up here, 12.2, right? And 10.48, yep. So I just got lost there. 13.2 kilowatts at 40% and 12.2 kilowatts at 40%. Now, the reason I'm identifying these two is because the rule says the next two of equal or lesser value at 40%, and that ends up being two different sizes of units. So they're both taken at 40%. The next 5 at 25%, the next 10 at 25%, the next two, whatever's remaining at 10%. So you have to be very organized. Notice I put brackets here. I can count them up. 4 times suite A, 6 times suite B, and 12 times suite C. The total suite demand for this installation ends up being just over 84 kilowatts. All right, so we'll set that number off to the side. Now we'll do the heat. We add all the heat together in the entire complex, and that gives us 88 kilowatts worth of heat. We apply 62118 subrule 3, which is the heat demand calculation for a residential occupancy. 82023D is the electric vehicle chargers, table 38. 10 times 5 kilowatts, and table 38 says 90%, so we have 45 kilowatts. Finally, the common use loads are taken at their ratings. Perhaps this apartment has a laundry facility. We add them all up, and we take 75% as indicated by 82023E, 31.5 kilowatts total common use demand. Well, let's add all of these up together. Total service, suite demand, heat demand, EVC demand, common load demand gives me 229.06 kilowatts. Now 229 divided by, it's a three-phase apartment, 208 times root 3 gives me 635.8 minimum service conductor ampacity. Table 2, I get a 1750 kc mil conductor, and table 13, 700 amp OC. Now what about the public panel conductor size? This too will offer a number of people some confusion because they'll say, wait a sec, Dave, haven't we already calculated this? And I'll say, yeah, you sort of have, but not really. Remember, you've just calculated the main service. Now you need to calculate the size of the conductors that will supply these loads that are coming out of the public panel. So 8202 subrule 4 is what we use. Lighting load, heat load, washing load, dryer, EVC, all of these are taken at their values. So there's no sort of reduction that takes place here. 100% of their values, and we've got a 97 kilowatt demand. Now, why have I divided it by 0.8? Well, remember at the very beginning of the installation, we said 100% rated gear for the main service, 80% rated gear for everything else. That means you need to inflate the value by 0.8. I don't care if it's done here or if you first work out the current and then divide by 0.8. Either way will come out with the same number. So 121.25 kilowatts is now my continuous load. I divide that by 208 times root 3, and I end up with 336.5 minimum public panel conductor ampacity. So table 2, 500 kc mil, good for 380, and table 13, 400 amp over current.